My name is Wright. I am a PhD student with Genesis. I'm working under Chris Power and Claudia Lagos. Now, some of you may remember me from the 2019 science meeting where, where at 14 followers on Twitter at the time, I took matters into my own hands and asked you all to follow me. Well, I wanted to extend a thank you to show that I've had my rise to fame. I have all of you to thank, so just to start with that. So today I will attempt to talk about a paper that we've recently submitted on trying to essentially disentangle the different mechanisms behind the quenching of satellite galaxies, in particular doing this with simulations so we can track this over orbital time. Now, when I refer to a satellite galaxy, I'm referring to a galaxy that exists in a group environment, so alongside a number of other galaxies, excluding any obvious central or galaxy or BCG that you may have. Now, both simulation and observational evidence, just so we're on the same page, has pointed towards the idea that satellites that exist in more dense environments are more likely to be quenched or see less star formation. Now, essentially, this is what you're seeing in this animation, and this is from the Eagle simulations, and you're seeing the fraction of galaxies that are quenched as a function of satellite stellar mass on the x-axis and host halo mass on the y-axis. And you can really see that quenched population becomes quite obvious towards lower redshift. Now, there have been quite a few different mechanisms that have been proposed to explain the quenching of satellite galaxies, but fundamentally, any of these mechanisms must somehow disturb the gas flows or the equilibrium of gas flows in a galaxy to somehow, to either reduce the cool gas mass in the ISM or interstellar medium, or to reduce the efficiency with which that gas could be converted to stars. Now, if you think of a galaxy that's in equilibrium, you would expect the gas inflow rate to offset the rate at which stars are being formed from the gas in the ISM and the rate at which gas is being removed via either feedback processes or perhaps environmental stripping. And in the case of satellite galaxies, one way that you could, I guess, offset this, disturb this equilibrium would be to experience reduced gas inflow or gas accretion. Now, this is often referred to as starvation or strangulation, and there's plenty of evidence, both observational and simulation-based, that this occurs. And I guess if you consider the other part of this equation here, you could also obviously directly remove gas from the ISM. And this could be environmental in nature, so you could have Rand pressure stripping, which is a hydrodynamical force, or you could have tidal stripping, which is more of a gravitational process. Also fitting into this kind of bracket, you could have, for whatever reason, enhanced feedback-driven outflows that would also contribute to this term. And the last mechanism that I'll just touch on is that you could also feasibly still have gas in your ISM, but the efficiency with which that is converted to stars could be reduced. Now, for the purposes of this work, we're really just concentrated on the mechanisms that will remove or reduce the amount of gas that is in the ISM. And where simulations really come in handy here, because we know that we have several lines of evidence that these different mechanisms are occurring, particularly in observations, but the question still really remains, how important is each of these different quenching mechanisms as a function of orbital time? So how can we add in this temporal dimension as opposed to the snapshots that we get with the observations to really understand how satellites are quenched? So to do this project, we've been using the Eagle simulations. I think Chris briefly mentioned the collaboration that we have here. I won't touch on this too much other than to say that this is a large scale, so cosmological simulation, and we see this, the formation and evolution of around a few tens of thousands of galaxies here. And the advantage, I guess, with this is that we have a sample of several thousand satellite galaxies that we can track over time. Now, what I'm showing here is that one thing that we really had to be careful with for this work, and that is how we select out the ISM of galaxies. Which is quite a sensitive process when we're talking about satellites in particular. Now I've used a method, I've been helped by Adam Stevens here to select out the ISM, and what you're seeing on the right is a comparison of the gas mass or the gas fraction of galaxies in Eagle as a function of stellar mass with this method compared to the X gas and X cold gas surveys. And you can see that with the gray line in Eagle for averaged over all galaxies, we get quite reasonable results, at least above 10 to the 9 solar masses. So that's just sort of to convince you that the simulation that we're using is somewhat reasonable. Now, of course, with this ISM definition, we can then also track the gas that enters the ISM, leaves the ISM, and the rate at which stars are formed from this gas. So we can kind of keep tabs on all of the different processes that are feeding the ISM and altering the star formation rate. Okay, so to start off with, I will take us through an example of a roughly 10 to the 10 solar mass satellite falling onto a roughly 3 by 10 to the 13 solar mass group in Eagle. So here the visualization, the purpley kind of color map is showing the gas density, and the more pale yellow color map is showing the stellar mass density. And as we start here, the satellite starts off isolated, so it's falling into the group at around a redshift of 1, and it's secularly forming stars. And we can pause here, which is kind of just before the galaxy enters the virial radius. Oh, Chris's face is covering the panel. You can see the radius. Can I move that? Okay, there we go. So as we rotate around here, we can see that we have disk structure. The galaxy is continuing to form stars. The morphology isn't too disturbed. But as we continue on the infall here, if I press that again, right, so we enter the virial radius, and as we spin around here, you can see that, so on the panels on the right, I'm showing the inflow rate and outflow rates normalized, or essentially the excess inflow and outflow rates relative to centrals that you would expect of the same stellar mass. So what this tells you is that as we've entered the virial radius, you can see that the inflow rate has dropped by about a factor of 4, and the outflow rate, which includes any gas that's leaving the ISM, so it could be enhanced feedback-driven outflows, or it could be stripping. But several lines of evidence are telling us that this is probably stripping. We can talk about that in question time if needed. But this outflow rate picks up by about a factor of 3 as well. And you can obviously see, I guess, in the animation that you have a fairly obvious tail of the cool gas that's being stripped off. So now as you play through here and the galaxy passes through pericenter and leaves the group again, if we pay it, we can sort of see that the gas envelope that we had before is no longer there. And the gas that does remain is very much within kind of where the stellar populations are. Focusing on I guess the right-hand panels again, we can see that the inflow rate, it's dropped off by a factor of 5 around by here, but the outflow rate where it peaked at pericenter has actually dropped off again, near back to baseline. So at this stage, the galaxy is essentially, if I rotate around, essentially just churning through the gas that it has left. Again, and as we go back into sort of the second pericenter, you can start to see that the outflow rate picks up again, it sort of peaks again, and you really don't have much gas left here. And the specific star formation rate drops to a level where you would consider the galaxy quenched. And this is just sort of how it fits into the group towards the end. So that's just one example, but obviously the example, oh, right, yeah. So I guess the points I want to highlight here are firstly that the gas accretion rate drops off around the first R200 crossing. So as soon as the galaxy enters the virial radius, it really is not experiencing much fresh accretion anymore. And secondly, that you can see that the outflow rates very obviously peak around the pericenters, where your orbital velocity is the greatest, and then your ram pressure stripping, which is proportional to the square of the velocity, is also greatest. Now, obviously we can sort of extend this to a statistical population, because we have quite a few satellite galaxies in this simulation. And one way that we did this, that we essentially wanted to parameterize the balance between gas flows on a statistical basis. So how we did this was that we split the galaxies into the galaxies that were net growing their gas reservoir. And for those that were net depleting their gas reservoir, we could calculate an indicative depletion timescale, taking into account all of the different gas flows that we were measuring. And we also can obviously classify a galaxy as quenched if its star formation is below a certain threshold. And we chose this delineating timescale between the slowly depleting and rapidly depleting galaxies based on a previous paper. So this is sort of the median quenching timescale that you expect. And I won't harp on about this for too long, other than to say, so this is the evolution of these, the breakdown of these different gas flow classes over the orbital timescale. So I've been helped out by Reese Poulton, who some of you may remember. He was part of the center a few years ago. So I use his code called OrbWeaver to parameterize or identify all of the different orbits. And so that allows us on the x-axis to kind of normalize our time by orbital time relative to first pericenter. So 0 is at first pericenter and 1 is at the second pericenter. And each of the different panels, the different columns are different mass satellite bins, and then the two different rows are different halo mass groups. So sort of smaller groups at the top rows, and then the larger groups on the bottom rows. And what I want to focus on here is that essentially you can very well predict the quenching of a satellite based on its stellar mass, its halo mass, and how many orbits it has completed in a group. So for the lower mass satellites, you see that regardless of halo mass, or for these two samples at least, you would expect the satellites to be quenched at first pericenter. For the more intermediate mass satellites, there is a difference between the two different halo mass groups. So in a larger mass group, a higher mass group, you would expect the galaxy to be quenched after first pericenter, and in the lower mass group, you would expect it to be quenched after second pericenter. It requires 2 pericenters to be quenched. And then lastly, for the more high mass satellites, you again expect them to be quenched after first pericenter in more massive groups. And in fact, in lower mass groups, you expect only 30% to be quenched after second pericenter. I'll leave with some conclusions there, and happy to take questions.